Okay, so the experiment to find the wavelength of monochromatic light. So the formula is n lambda is d sine theta. Okay, n lambda is d sine theta, and to get d, it's 1 over the number of lines per meter. Now the number of lines per millimeter is given to you, or per centimeter is given to you on the grating. So we can work it from there. We'll look at an example later. Okay, so our apparatus, we just have a laser, grating, and the screen. Okay, and if we look at how we get our angle, okay, we measure the distance from the grating to the screen, which I'm calling the adjacent. We measure the distance from the center image, n equal to 0, and we'll know that because that's the image that will be there before you put in the grating, to the first order on the right, for example. That would be O, opposite O, and from that we can get the angle tan theta is opposite over adjacent. So we can get our angle, we can get D, we can get n. In this case it's n equal to 1, but it could, if you take the second order image or the third order image, it will be n equals 2 or n equals 3 or whatever, and you're in business. Okay? So if we go around here and we look at our apparatus, okay, our setup. Okay? So here's our setup, right? So we have our laser, which is a monochromatic collimated light source. So monochromatic, one color, collimated, a narrow beam. Okay, a narrow beam. Okay, we'll have our grating there, and we have our screen. So before I put the grating in, as you'll notice, before I put the grating in, we have 1 point, and that is the n equal to 0 point. So if you're asked how do you know the n equal to 0 point, it's the point before you put the grating in. Okay, we put the grating in. This is the grating. Okay, and we get our series of lines, as you can see. Okay, we get a series of lines, n equal to 0, 1, 2, 3, 4, and so on. Okay, and you do the measurements as we just said. Okay, now what's interesting is that's 80 lines per millimeter. If I increase it to 600 lines per millimeter, okay, go up here, the distance between the slits will be smaller. The wavelength will be the same, n lambda on the left will be the same. The distance between the slits will be smaller because it's more than per millimeter. So therefore, for d sine theta will have to stay the same because n lambda on the left is the same. So the angle should be bigger. So if you make the distance between the slits smaller, the angle should be bigger. So let's see. If I put in 600, okay. Now I put this down. Okay, put in 600. Okay, and indeed it is, 1 second now, bigger, because look, that's the distance from the n equal to 0 to the n equal to 1. So a huge increase, because the distance between the slits was much, much smaller. Okay, you can take it to extremes, and we'll look at this in a minute. The Young slit experiment, so I put 2 slits here now. There are only 2 slits in this one, okay, and they're quite wide apart, as you can see. Okay, so if you look at the screen, all you can see is what looks like a blur. But if we go up close to the blur, it looks like a blur. Unfortunately, not zooming for us very well. Okay, but that actually is, I think you can see it there just about, it's a series of dots that are very, very close together. That's when D is very large. Okay, so we're clear. There's a very good experiment, a very good clip that you're going to watch in a minute, which goes through this again. Be sure to watch it.